So what we're going to start right now is our next type of confidence interval. The type of confidence interval we just covered was the Z interval from U. And the Z interval from U, the one thing I want to point out or want us to remember is in the Z interval from U, the one we talked about last time, you had to know what sigma was. Okay, so let's talk about something here and then we'll return to confidence intervals. So in order to do the next type of confidence interval, we have to know something about another type of random variable, right? So we've talked about a bunch of different types of random variables. We've talked about binomial random variables, and we've talked about normal random variables, and a few others. There's another type of random variable, and it's called the T random variable. Okay, and the T random variable, it's always good when this part of the unit comes near St. Patrick's Day because there's a little bit of at least something of an interesting history with the T random variable. The T random variable was developed by a gentleman named William Gossett. And William Gossett, he worked for Guinness Brewery in Ireland. And hence the tie-in with St. Patrick's Day. That's all there is to it, really.
He's not a leprechaun?
Not that I know of, no. And what he did for Guinness Brewery was he did quality control. And anytime in any business people are doing quality control, you need statisticians and people like that. And William Gossett was a statistician, and in 1908, he came up with this stuff that I'm going to show you today. He came up with the T distribution and kind of used it in the same context, or a similar context, as what we're going to use it today. And so he wanted, as most statisticians and academics and people like that, they want to publish their results. So he was going to write an article and wanted to publish his results. And the Guinness Brewery did not want him to use his name in this article, right? Because then all its competitors would know that Guinness is using quality control and using statistics and things like that, and they didn't want their competitors to know that. And so when he published this article, he used a pen name. You guys know what a pen name is? It's like just, yeah. And his pen name was Student T. I'm not sure exactly why he chose Student T, but that was his pen name. And so this distribution that he outlined in this article became known as Student's T distribution, or the T distribution, or T random variables. So that's about as interesting as it gets when it comes to the development of random variables, I think. At least maybe for you guys. So just like there's an infinite number of normal random variables, right? Like you can have a normal 0, 1 random variable, and you can have a normal 1, 2 random variable, and a normal, there's an infinite number of them. It's the same thing that goes for T random variables. There's an infinite number of them. The thing you have to know about T random variables is what are the degrees of freedom. So the thing that characterize these are their degrees of freedom. That's what we call DF, degrees of freedom. All of the T densities are centered at 0, and they're all bell-shaped. They're all centered at 0, and they're all bell-shaped. So they kind of look like a normal 0, 1. They kind of look like a Z distribution, a Z density. The degrees of freedom is going to describe the shape, basically, if you're looking at the density. And all of them have fatter tails than the Z. So they all have a little bit more area out in the tails and a little bit less area in the middle than a Z does. Now, how much more is characterized by the degrees of freedom? And I'm not giving you guys all the details, but you don't really want the details, I don't think. The thing to remember is as the degrees of freedom get big, so as the degrees of freedom get big, the T density gets really, really close to the Z density. And so the next picture I've got up here is going to illustrate that. So what I've got here in this picture is I've got a normal 0, 1, so a Z, and then I've got a T with 1 degree of freedom, a T with 5 degrees of freedom, a T with 20 degrees of freedom, and a T with 50 degrees of freedom. So I've got 5 different density curves up here in this graph. Which one of these is the Z? It's hard to tell. It's the normal 0, 1. So is the Z going to be the highest or the lowest out here in the tail, in this right tail? It's going to be the lowest, right? The z has the least amount of area in the tails. So the z is going to have be the lowest right here, which means what about here in the middle? It's the tallest, right? Because they all have to have a total area of 1. They're all valid density curves. They all have to have a total area of 1. And so you can just kind of go in reverse order, right? So the z has the least amount of area in the tails and the most area in the middle. Go to the opposite end. The t with 1 degree of freedom is going to have the fattest tails. It's going to have a bunch of area out here in the tail. And it's going to have the least amount of area here in the middle. And with the one with 1 degree of freedom, you can see that pretty well, I think, right? And then from that point, it's just kind of varying degrees. So if you go to 5 degrees of freedom, that's this one. If you go to 20 degrees of freedom, it's this one. 50 degrees of freedom is this one. The one with 50 degrees of freedom, you can barely tell the difference between the z and the t with 50 degrees of freedom, right? So they're pretty close. Yeah, they're pretty close. And if you were to, if for some reason I was to draw a t density curve that had 1,000 degrees of freedom or 10,000 degrees of freedom, it would almost be almost exactly where the z is. Okay. It never actually gets there, but it gets really, really close. I guess in theory, if you could have an infinite degrees of freedom, it would be the z. Yeah. That's a good point. So any questions about that? So the thing to remember about t's, all these different t densities, every one of these is centered at 0, right? Every one of them is bell-shaped. The only difference is as the degrees of freedom if the degrees of freedom are small, you're going to have, more area out in the tails. And as the degrees of freedom get bigger, you've got less area in the tail, more area here in the middle. Okay? Okay, so back to the problem that we've mentioned, I don't know, a couple yesterday, I think it was. We mentioned when we're doing confidence intervals, in reality, we're probably not going to know what sigma is. Right? When you're doing a confidence interval, when you collect data, nobody just kind of comes up to you and whispers over your shoulder, sigma's 3 or something like that. You don't know. You don't know what sigma is oftentimes. You don't know. But yesterday, to use that formula that we had, you had to know what sigma was. It was in the formula. And so what people would be inclined to maybe think about doing is they'll say, okay, so if I don't know sigma, I don't know the population standard deviation, but if I've got a sample, I can always calculate S, right? The sample standard deviation. I can calculate that statistic. So people say, okay, well, maybe what I'll do is instead of using sigma, I'll just use S, because I can always get S. If I've got a sample, I know what S is. And that makes sense, right? But you guys tell me this. If you don't know sigma, if you don't know the population standard deviation, and you replace it with the sample standard deviation, are you introducing more variability, or are you taking away variability? You're introducing more variability, aren't you? Right? If you use another, S is not exactly going to be what sigma is. And so you're introducing more variability. You're introducing more uncertainty. So to account for this extra uncertainty, what we do is instead of using a z critical value, anybody want to guess? We're going to use a t critical value, right? Because what that t density does is it's got more variability to it than a z. It's got fatter tails. It's got more area out in far away from the mean. And so by using a t critical value, we're accounting for that extra bit of uncertainty. So that's really what's going on. So the only difference here, so when we introduce what's called the t interval from u, it looks very similar to what we had last time. Looks very similar to what we had last time. We've got x bar plus or minus a critical value times a standard deviation divided by the square root of n. The only difference is instead of the population standard deviation, we're using S. And instead of a z critical value, we're using a t critical value. Which begs the question, okay, well, there's a bunch of different t densities, right? There's a t with 1 degree of freedom and 2, and there's a bunch more than that. Which degrees of freedom should we use? Well, the answer is you should use degrees of freedom is equal to n minus 1 for this procedure, where n is the sample size. So if you have a sample of size 26, use 25 degrees of freedom. If your sample is size 43, use 42 degrees of freedom.
Because that's the n minus 1.
That's it. That is n minus 1. That's exactly right. And so what that is saying is, as the degrees of freedom get big, this t critical value is going to get pretty close to the z critical value, isn't it? Yeah. So that's what's going on. In terms of assumptions, x bar normal, we still have that assumption. That was the same as last time. Data comes from a simple random sample, same. The only difference between these assumptions and the assumptions we had last time, we're assuming that sigma is not known. It's the only difference. And so when should you do the t interval, and when should you do the z interval? If you know sigma, do the z interval. If you don't know sigma, use s and do the t interval. That's the only difference. Okay?